Suppose you have a sequence of functions that converge to a limit function. If you take the derivative of that entire sequence, does it converge to the derivative of the limit? For integration, the answer is remarkably straightforward. When a sequence of functions converges uniformly, the total area underneath them is strictly preserved. You can cleanly swap the order of the limit and the integral without breaking the math. Differentiation behaves completely differently. Even if a sequence of functions converges uniformly to a perfectly smooth limit, there is zero guarantee that the derivative of the sequence behaves predictably. The tangent lines can spin wildly. Integration is inherently a global property. It aggregates values across an interval, which naturally smooths out microscopic chaos. Differentiation is a purely local property. It measures an exact rate of change at a singular point, meaning it actively amplifies tiny oscillations. Relying purely on the uniform convergence of the original functions is a mathematical trap when calculating rates of change. To safely swap limits and derivatives, we need a stricter mathematical rule to tame the slopes. We see exactly how uniform convergence deceives us by looking at Walter Rudin's counterexample in Principles of Mathematical Analysis, example 7.5. We define a sequence of functions as the sine of n times x over the square root of n. This graph shows the behavior of that exact sequence. As the value of n increases toward infinity, the denominator grows, causing the wave's amplitude to shrink entirely. The sequence converges uniformly to a completely flat limit function of 0. But look what happens when we calculate the derivative of that sequence. Applying the chain rule pulls an n out of the sine function, leaving us with the square root of n times the cosine of n times x. If we evaluate this rate of change precisely at the origin, where x equals 0, the cosine term becomes 1, leaving just the square root of n. As our wave flattens to 0, the slope at the origin actually explodes toward infinity. Our original wave flattened out completely, yet its rate of change grew boundlessly. Uniform convergence of a function completely fails to tame its slopes, meaning we cannot assume a limit function is differentiable without applying a new constraint. In Theorem 7.17, to guarantee a differentiable limit function, we must demand the sequence of derivatives converges uniformly. But there's a counterintuitive trade-off. Strictly controlling the derivatives means our original functions only need to converge at one single point, x sub 0. The proof relies on the mean value theorem. If you nail down a sequence of functions at a single anchor point and force their slopes to be uniformly close, the functions are physically tethered together. They cannot drift apart. With convergence everywhere established, the proof must show that the new limit function is actually differentiable. It does this by explicitly defining the difference quotients for both the sequence and the limit function. This diagram illustrates the exact geometry of equation 31. The difference quotient is simply a dynamic secant line cutting through the curve. As point t approaches x, the points slide closer together, and that secant line becomes the exact tangent slope. Now we have two limits happening simultaneously. N is approaching infinity, and t is approaching x. To finalize the derivative, we have to swap the order of these limit operations. Think back to our previous proofs. What mathematically justifies this swap? It's Theorem 7.11, which permits the exchange because our difference quotient converges uniformly. Controlling the sequence of slopes provides the necessary constraint. It ensures the functions converge everywhere and forces their resulting limit to be differentiable. Rudin includes a crucial remark. If we assumed all sequence derivatives were continuous, we could bypass this proof via the fundamental theorem of calculus. However, Rudin's mean value theorem method is deeper, proving the relationship holds even if the sequence of derivatives is entirely discontinuous. This specific theorem acts as the core engine for advanced mathematical analysis. It is the exact rule that gives us permission to slide a derivative operator directly past an infinite sum symbol, allowing us to differentiate power series and Fourier series term by term. Not all limit processes are equal. Because differentiation is so sensitive to localized change, it is inherently volatile. To prevent chaos from breaking the limit, you have to strictly police the uniform convergence of the slopes. If you found this breakdown helpful, subscribe to the channel for more step-by-step deep dives into the proofs and structures behind advanced mathematics texts.